First, NASA has broken their silence. They will release images of 3I Atlas on Wednesday via livestream.
The images recently released of 3I Atlas by Mars Reconnaissance orbiter using its HiRISE camera mark a critical moment in our exploration of the solar system's interface with the broader galaxy. On October 2, 2025, HiRISE captured views of the interstellar comet from about 30 million kilometers, roughly 19 million miles away, the closest vantage yet from a spacecraft orbiting another planet. These images allow us to witness this visitor from beyond our solar system in unprecedented clarity and to reflect on what its passage signifies for science, exploration, and our understanding of the cosmos. Before we start, smash the like and subscribe buttons for more updates. What immediately draws attention in the HiRISE frames is the plume and tail structure of 3I Atlas. The comet's coma appears as a fuzzy, luminous body surrounded by dust and gas, and in one of the exposures, the plume extends for around 3,000 kilometers, a striking scale given the object's estimated nucleus of only a few kilometers across. The geometry and orientation of this plume are puzzling. Instead of pointing strictly away from the sun, as solar radiation and wind might suggest, it appears in the direction of motion of the object. This is a subtle but meaningful clue that the physical processes at play may differ from those of typical solar system comets, or at least that the viewing geometry is unusually favorable to detect features rarely seen. Equally meaningful is the fact of 3I Atlas itself. The designation 3I signals that this is the third confirmed interstellar object known to pass through our solar system, following 2I Borisov and 1I Oumuamua. Its entrance into the inner solar system on a hyperbolic trajectory marks it as an unbound visitor. It came from outside and will continue outwards, never to orbit the sun. The orbit, speed, and chemical signatures all testify to this extraordinary provenance. The HiRISE images thus offer more than mere spectacle. They open a window into materials and processes that formed in completely different star systems billions of years before our own planetary neighborhood emerged. In observing 3I Atlas, scientists are peering at a fragment of cosmic history carried across interstellar space that has only now passed close enough for detailed study. The materials ejected from its surface as it warms while moving through the inner solar system can tell us about the conditions in distant protoplanetary disks, or about how objects from one star system evolve when cast adrift into the galaxy. These images also highlight the remarkable precision and flexibility of space missions. The Mars Reconnaissance orbiter, designed for studying Mars and its surface geology, turned its powerful HiRISE instrument to an object that happened to pass by Mars. That opportunity was seized, yielding a vantage point otherwise unobtainable from Earth or conventional solar orbit telescopes. This kind of opportunistic science demonstrates how multi-purpose missions and flexible instrumentation can pay surprises in the exploration of the solar system and beyond. In terms of the comet's composition and activity, the images provide context that complements other observations. Spectroscopy and follow-on studies have shown that 3I Atlas is unusually rich in carbon dioxide and contains volatile materials like water, carbon monoxide, and even atomic nickel in its coma. The HiRISE images, while not resolving the nucleus itself, which at tens to hundreds of meters across, is below the resolution limit at 30 km pixel, give us the shape and structure of the coma and dust plume, which in conjunction with the spectroscopic data allow us to estimate dust loss rates, erosion of surface layers, and perhaps even structural fragility of the nucleus. Why does any of this matter? For one, 3I Atlas's passage underscores the fact that the solar system is not isolated. Material from other parts of the galaxy drifts into and through our neighborhood. Each such visitor is a sample of other star systems brought to our doorstep, albeit fleetingly. By studying them, astronomers build a broader statistical understanding of the diversity of small bodies across the galaxy. We can begin to ask, how typical is the chemistry of our own comets? Are objects like this rare, or have we simply lacked the detection sensitivity and the right trajectory alignment to see more? Secondly, the event pushes the boundaries of planetary science. Most cometary studies focus on objects formed in the outer reaches of our own solar system. But interstellar objects carry a memory of the environments around other stars, perhaps formed under different metallicity conditions, in different dynamical regimes, subject to different radiation environments and stellar winds. By comparing what we see in 3I Atlas with solar system comets, scientists can test hypotheses about solar system formation, the uniqueness or lack thereof of our chemical inventory, and the evolution of small bodies in interstellar space. Thirdly, the images and data encourage development of new mission architectures. The fact that a visitor like 3I Atlas can be glimpsed by a Mars orbiter highlights the potential for remote observational campaigns and opportunistic flybys of interstellar wanderers. It forces the question, what would it take to chase down one of these objects more deliberately? While currently a direct interception remains technically challenging, given the high velocities and unpredictable trajectories of interstellar objects, this is a compelling incentive for future mission planning and investment in rapid response capabilities, wider sky surveys, and more agile spacecraft. The plume observed by HiRISE has particular dynamical interest. A forward-pointing excess of gas and dust raises questions about the microscopic physics at work. Are we seeing jets directed by rotating vents on the nucleus, outgassing asymmetrically? Is the dust-gas mixture being shaped by solar radiation pressure, solar wind effects, or even local microgravity and spin effects? In one analysis, the plume's forward direction leading the object could hint at dust being accelerated ahead of the body, or perhaps a lag in gas expansion relative to the object's motion. That kind of subtlety holds clues to nucleus rotation state, vent geometry, and potentially the internal structure of the object, all of which are enormously difficult to infer for standard comets. Another implication lies in the size and risk assessment of such objects. Though 3I Atlas poses no threat to Earth, its closest approach to Earth is about 1.8 astronomical units, 170 million miles. The study of its trajectory and behavior refines our understanding of small body dynamics in the solar system, including interstellar entry. It also illuminates detection thresholds. Previously, only 2 interstellar objects had been confirmed, but each new one sharpens the statistical table of how many such interstellar bodies pass through our region and how many we might recognize in future. Yet perhaps the most humanly resonant implication is the sense of perspective. The captured images provide a tangible connection to the vastness of space, to objects born in star systems long gone and traveling for eons beyond their origin, now passing through our domain for only a moment. The idea that we can photograph, chart, and analyze such a wanderer speaks to the rapid progress of astronomical technology and the global scientific enterprise. It invites philosophical reflection that our sun and planets are but one node in a dynamic, galaxy-wide system of material exchange and movement. In practical terms, the dataset emerging from HiRISE's observations will be paired with ground-based telescope campaigns and space-based observatories like James Webb Space Telescope and Hubble Space Telescope. These combined observations will enable modeling of particle sizes, coma expansion velocities, dust-to-gas ratio, nucleus albedo, and potentially thermal inertia of the surface layer. Each piece helps complete the puzzle of how 3I Atlas differs from or resembles solar system comets. The Mars orbit vantage is particularly beneficial because the geometry between Mars, the comet, the Sun, and the spacecraft allowed an angle of view that is different from the Earth-based line of sight. That geometry helps separate effects that otherwise might be hidden from Earth. For instance, shadows cast in the dust coma, asymmetry of the tail, and evolution of the plume orientation as the object moves deeper into the inner system. The fact that HiRISE was able to detect it despite not being optimized for moving small body tracking at long exposure lengths, is testament to the ingenuity of mission operators and the flexibility of spacecraft instrumentation. Given that 3I Atlas will not remain in view of telescopes indefinitely, the timing of the HiRISE images is fortuitous. Having captured the comet near its closest approach to Mars, and before it recedes too far, the dataset will serve as a cornerstone for ongoing analyses. Because the object will continue on its hyperbolic trajectory and depart the solar system, the opportunity to study it in situ is irretrievable. That impermanence adds urgency to the observations and poignantly underscores the fleeting nature of such encounters. From an educational and outreach perspective, the release of these images by NASA generates excitement and public curiosity. Objects from outside the solar system inspire wonder and underscore the fact that astronomy is not confined to local space, but reaches into the galaxy. The imagery gives educators and communicators a concrete reference point, a visible object captured in space that tells a story about interstellar travel, cosmic origins, and the interconnectedness of planetary systems. Moreover, the success of this observation will likely influence the design of future sky surveys. Detecting interstellar objects earlier and tracking them sooner improves the window for observation and possible spacecraft mission proposals. The fact that 3I Atlas was caught only after it had entered the inner system suggests that there may be many more such visitors lurking unnoticed. As detection technologies improve and as space agencies coordinate rapid responses, we may treat interstellar comet visits as routine science opportunities rather than serendipitous surprises. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on NASA's new HiRISE 3I Atlas photos and outcome this year? We want to hear from you. Thank you for watching and see you next time.